Okay, thanks, Chad, and thanks to the organizers for inviting me here. Let me see if I can get my slides started. Okay, can you see those?
Looks good.
All right, so my talk today, which is very similar to the one that I did online, but a little shorter, it's called Beyond Bare Detection to Biological and Geological Indicators. I'd like to start by reminding people that the search for life out there in the universe has been going on for several decades, 6 of them in fact. 2 of the early pioneers in this were Carl Sagan and Frank Drake. And of course, this is the Sagan workshop that you're attending, named in Carl's honor. Sagan and Drake co-convened a meeting at the Green Bank Radio Observatory in 1961, which was focused on actually not just the search for life, but the search for intelligent life in the universe. And, you know, it's kind of strange in a way. If you think about it, logically, we should have started looking for life first and intelligent life after that, because intelligent life is a subset. But it turns out that the technology needed to look for intelligent life was easier to develop. Radio telescopes have been around for many decades now, and the technology that we need to look for simple life is much more difficult. And we'll talk some about that a little bit in my talk and maybe more in the panel discussion. Let me give you the outline for the talk. I'm going to start with talking a little bit about the basic requirements for life, because when I give this talk in a seminar, usually most of the questions are on that aspect. So let me say some things there. I'll talk a little bit about the definition and boundaries of the habitable zone, but that's shortened compared to the online talk because it gets kind of technical. And in fact, there's not that much technical detail in the online talk either, but there's lots of papers on that. And then finally, I'll talk about atmospheric biosignatures and how to look for them with missions that are being planned. And that, I think, is the part that excites most of us. So I want to spend some time on that. All right, let me start with the requirements for life. I'm going to list 4 of them here. 3 are on this slide. Number 1, you need a planet with a liquid or a solid surface. No gas giants allowed. And you know, that in that sense, I'm more pessimistic than Carl Sagan. If for those who watched Cosmos or read Carl's book on the series, Sagan he showed pictures of these giant floaters in Jupiter's atmosphere, simulated floating creatures that could adjust their altitude in the atmosphere by changing the pressure inside their bloated bodies. But you have to ask yourself, how would something like that evolve? Life, we think, starts from a simple single-celled form. And on a planet like Jupiter, there's no stable pressure temperature regime on which life could originate. So I think we are talking about rocky planets. And most of us seem to agree on that. Second requirement is you need a thermodynamic free energy gradient to drive metabolism and growth. Stellar radiation provides much of the free energy today, although there are many microbes that get by with chemical sources of free energy. That's also non-controversial. I think any theory of life requires that you have a power source for it. The third requirement that I've listed here is availability of carbon and other bioessential elements. I'm going to assume carbon-based life in this talk, so that's a little bit anthropocentric, but on the other hand, there are lots of good chemical reasons why carbon is used by life. It forms bonds much more easily and in a much wider variety of ways than other elements. So I personally think that if we find life elsewhere, it will also be carbon-based. Then the fourth requirement gets a slide of its own, because that's really what a lot of this talk is focused on. All life on Earth requires liquid water during at least part of its life cycle. There are spore-forming organisms, for instance, that can get by for long periods without it, but they need liquid water to metabolize and reproduce. And so, that is more controversial. There are astrobiologists who speculate that there might be life on Saturn's moon Titan in the liquid methane lakes there. And so we don't really know that, but there's also good chemical reasons why water it's a good solvent. It's very polar. Oxygen is the third most abundant element in the universe, so water is probably abundant out there. And then the other thing I'll add is that if it's not water-based life or carbon and water-based life, I think we're going to have a hard time recognizing it. We can come back to that in the discussion. The second point, the third point on the slide is that subsurface water is not important for this talk or for astronomers in general. There's a lot of astrobiologists who are interested in subsurface life in this solar system, either on Mars or Jupiter's moon Europa or Saturn's moon Enceladus. But these are places where we can go and are going with spacecraft, and we can look for that life directly. If you have looking for life on an exoplanet, subsurface life is probably undetectable because to be detectable, that life needs to modify the planet's atmosphere in a way that we can detect spectroscopically. So I think that requires that you have water at the surface, liquid water at the surface. All right, that leads to the definition of two terms. One is this parameter eta sub Earth, which the astronomers have defined. It's the fraction of stars that have at least one rocky planet in their habitable zone. And for those who are familiar with the Drake equation for looking for intelligent life, eta sub Earth is very similar to n sub e, the number of Earth-like planets per planetary system in the Drake equation, except eta sub Earth is normalized to be between 0 and 1. And this is, of course, what we need to know to design these big space telescopes that I'll mention at the end, to look for life out there. And it's also what the Kepler mission was designed to figure out. Kepler's primary purpose was actually to determine eta sub Earth, so we'd have some idea of how frequent Earth-sized planets are. The last point there is I'm going to argue that we should be conservative when calculating eta sub Earth because we don't want to undersize the telescopes that we're working on. All right, the other term that is involved there is the habitable zone. Chad already mentioned that I've worked on that concept on and off for a long time. I only learned just recently, within the last year, that the term habitable zone goes back much farther than I had realized. I had been attributing it to Sushu Huang in 1951, I think, but Ralph Lorenz discovered in this old book by Walter Maunder, Are the Planets Inhabited, that Maunder defined the habitable zone in this book. And this is the same Maunder that's well known amongst astronomers and earth scientists for his research on the Maunder minimum, the sunspot minimum between 1645 and 1715. I was first exposed to the term habitable zone reading two papers by a planetary scientist named Michael Hart back in the late 1970s. I was a graduate student at University of Michigan at the time. And Hart wrote his first paper in 1978. He defined the habitable zone as the region around a star in which an Earth-like planet could maintain liquid water on its surface at some instant in time. And then he also defined what he called the continuously habitable zone, or CHZ, the region in which a planet can remain habitable for some specified period of time, which we usually take to be 4.6 billion years for our own solar system. So if you can see my cursor here, the habitable zone moves outward with time because all stars brighten as they age and convert hydrogen to helium. Early type stars brighten faster than late type stars. But if the habitable zone at some time T0 went from here to here, then at some later time when the star had brightened, it would go from here to here, the overlap between these two regions is what Hart defined as the CHZ. What were Hart's conclusions? In the 1978 paper, he built a model and used it to estimate the width of the habitable zone around the sun. He concluded that the 4.6 billion year continuously habitable zone around our own sun is quite narrow. The inner limit in his model was 0.95 AU, where the planet would experience a runaway greenhouse, and the outer limit was at 1.01 AU, where the planet experienced runaway glaciation. So just barely beyond where the Earth is today. And then in the second paper, in the following year, Hart took this same model and applied it to planets around other types of stars, and he concluded that the continuously habitable zones around other spectral types are even narrower, or in some cases non-existent. So the pessimists out there, there are pessimists amongst astronomers as well as in other areas of life, and they picked up on this, and you can still find that in some older astronomy textbooks, that Earth may be the only habitable planet in our galaxy based on these types of calculations. Well, this was, I was dismayed by this because I was in graduate school. I was a big fan of Carl Sagan, and Sagan, of course, thought that life was widespread in the universe, and even intelligent life might be widespread. So I started immediately, wondering if there might be flaws in Hart's model or in his reasoning, and that was one of the main things that got me to work on this on and off for a long time after that. So there were, I would argue, problems in Hart's model. He concluded incorrectly that a fully glaciated planet could never deglaciate by building up CO2. And I'm going to talk about more about that in the next slide, but we actually have empirical evidence that that is not the case, because if you study the geologic record, you'll learn that we think that the Earth actually froze over entirely or almost entirely at least 2 or 3 times in its history. And it appears to have recovered from that by building up CO2 in its atmosphere, leaving these deposits called cap carbonates that show that the feedback mechanism does work. And second of all, there is this negative feedback mechanism, which actually Leslie Rogers described pretty well in the earlier session today. I'll describe it myself with the help of this slide here. Leslie mentioned the carbonate-silicate cycle, and that's what's shown here. It's part of the carbon cycle, and the carbon cycle confuses people because it's actually more than one cycle going on. When we say carbon cycle, most people think of the organic carbon cycle, which is photosynthesis going in one direction and respiration and decay going in the other. But that's not what we think controls the Earth's CO2 level on long time scales. Rather, it's controlled by the inorganic carbon cycle, also called the carbonate-silicate cycle. And it's shown on this cartoon here. If we start on the left, CO2 dissolves in rainwater, gives a weak acid, carbonic acid, which is weak enough that you can drink it. That's the acid in soda pop, but it's strong enough to dissolve rocks on the continents. And we care here about silicate rocks, represented here by the simplest silicate mineral, calcium silicate or wollastonite. Calcium silicate plus carbonic acid or CO2 and water yields calcium ions and bicarbonate and dissolves silica. These ions collect in streams and rivers and flow down to the oceans, where various organisms use them to make shells out of calcium carbonate. And then the organisms, the planktonic foraminifera, fall down into the deep ocean. Most of the shells dissolve because the deep ocean is more acidic than the surface ocean. But some of them form sediments on the seafloor, carbonate sediments. Then the seafloor is not just sitting there, it's spreading away from the mid-ocean ridges and at some plate margins. The seafloor is subducted, the carbonate sediments are dragged down. Some of them are scraped off, but some of them are dragged down to deeper depths where the temperature and pressure are higher, and calcium carbonate recombines with silica, which by this time is the mineral quartz, to reform calcium and magnesium silicates and release gaseous CO2. And that CO2 then escapes to the atmosphere through volcanism. So what would happen if we think, if the climate was to freeze over, the ocean would freeze, the hydrologic cycle would slow down dramatically, and silicate weathering would slow down or stop entirely. So the loss process for CO2 would stop, volcanism would continue. There's also other types of volcanism. This is arc volcanism here, but there's hotspot volcanism like you see in Hawaii, and there's volcanism at the mid-ocean ridges. So in short, CO2 would be put back into the atmosphere but not removed. And so the planet would accumulate enough CO2 until eventually you get enough greenhouse effect to melt the ice. And in modern models of the greenhouse effect, if you do it properly, you find out that it's pretty easy to deglaciate a frozen planet. Hart just chose a very poor model for the greenhouse effect. There are caveats to this, one of them being that if you have a planet with a low volcanic outgassing rate or low stellar insolation, you may not get a steady state solution. You can get limit cycling behavior where the climate oscillates back and forth between global glaciation and warm states on different time scales. And this has been shown, so parts of what I'm going to call the habitable zone may be less habitable than other parts depending on planet size and stellar distance from the star. All right, so this is how we define this term, how we calculate that habitable zone. We assume that CO2 builds up in a planet's atmosphere when the planet gets cold, and that pushes the outer edge of the habitable zone much farther out than where Michael Hart had it. The inner edge in our models is actually the same as his inner edge. It's at about 0.95 AU, but the outer edge is out towards Mars's orbit. Now this diagram here is an old one. This is based on some calculations that our group did in 1993 when there were 9 planets in the solar system. So I've had to X one of them out of this very pretty diagram, which was made by some Europeans, not by me. Notice that this, it's called the ZAMS habitable zone. That's the zero age main sequence habitable zone. Remember that stars change brightness as they age, so you have to pick a time in the star's evolution to draw a diagram like this. The x-axis is the radius of the orbit in astronomical units. The y-axis is the mass of the star relative to the sun. And what you see here is that at zero age main sequence, 4.6 billion years ago, Earth was smack dab in the middle of the nominal habitable zone. You also see that the habitable zone is wide. Its width is comparable to the spacing between terrestrial planets in our own solar system. So if planets in other systems are spaced like they are here, then the chances of having a planet in the habitable zone are pretty good. Of course, you know, the data have been coming in. You've been hearing about the data on other planetary systems, and so far the ones we've seen don't look much like our own. But you just heard in the last talk that that's probably at least partly a selection effect. So we really don't know the answer on that. Those limits that I just showed you were based on climate models that we did. There are researchers I've found in my career that don't trust theorists. And so there are always skeptics out there. So to satisfy the skeptics, you can also define empirical limits on the habitable zone. We can look at Venus, this upper diagram. That's a picture, SAR radar image of Venus taken by the Magellan spacecraft, which can see through the clouds at radar wavelengths. And we don't see any fluvial features there. We think that Venus was resurfaced between 500 million and 1 billion years ago. So the evidence is that Venus has been dry since something like 1 billion years ago. That we call that the recent Venus limit. On the other hand, if we look the other direction, look out at Mars, we see that there are lots of fluvial features on the surface of Mars, which we think are 3.8 billion years old or older. And so Mars, you know, it looked just to remind you, it looks like it's out of the habitable zone back at that time in this diagram, but actually our calculations of the outer edge are probably too pessimistic, because early Mars looks like it was in possibly habitable. Here's a more recent version of the habitable zone, where this is from work done by my postdoc Robbie Kopparapu and then graduate student Ramses Ramirez back around 2013 and 14. So what they did is they updated the older model with newer absorption coefficients, which are talked about in the online talk. We've also replotted the habitable zone. The x-axis is now the amount of starlight on the planet relative to sunlight on Earth, and the y-axis is effective temperature of the star rather than stellar mass. Venus, Earth, and Mars are shown here. But doing the diagram this way sort of blows up the habitable zone, so you can see what's going on around different types of stars. And you can see also that this habitable zone by this time is now populated with various objects, mostly from the Kepler catalog. I think Gliese 667c was a radial velocity planet. Now we define two different habitable zones here. This region between the runaway greenhouse and the maximum greenhouse. The maximum greenhouse I skipped over. There's a limit to how much warming you can get out of CO2, and that defines the maximum greenhouse. That's what we call the conservative habitable zone. If you don't trust theorists and you think clouds might save you or something else on the inner edge, then we also define the optimistic habitable zone going from the recent Venus limit to the early Mars limit. And you notice that some of these Kepler objects are in the conservative habitable zone and others are in the optimistic zone. The most recent version of this habitable zone plot, I should mention that these plots, these pretty plots, are done by my former graduate student, Sonny Harmon, who's now out at NASA Ames, who's an accomplished graphics artist. Now, what Sonny has done in this plot, this is a year or two old, but it's pretty up to date, is to remove all the planets greater than 1.6 Earth radii. I didn't follow the whole workshop here, but we think most planets greater than 1.6 Earth radii are not rocky. In fact, Leslie Rogers had a paper by exactly that title. So if you exclude rocky planet candidates to less than 1.6 Earth radii, this is what you get. Notice at the bottom here, the TRAPPIST-1 system here, 3 of the TRAPPIST-1 planets are within the conservative habitable zone, 1 is in the optimistic habitable zone, and the other planet of great interest is Proxima Centauri b, which is in the conservative habitable zone. The TRAPPIST-1 planets, of course, were found by transits from the ground, and Prox b is radial velocity. But so that Prox b is TRAPPIST-1 you heard already today, that's a target for JWST, and Prox b is a target for the ELT using this high dispersion spectroscopy that Jane Birkby talked about earlier. All right, so that brings me to the third part of the talk, atmospheric biosignatures and how to look for them. I want to talk here about direct imaging, which you've already heard about from several speakers, and you'll probably hear about it more from Courtney and from Scott Gowdy, because they were involved in recent studies. But most of what we can do today is get spectra of transiting planets. And even with JWST, it'll do a much better job on transit spectra, but you're still limited to planets that transit. In direct imaging, we want to block out the light from the star and look for either the reflected light or the emitted IR radiation from the planets around it. So that, I will argue, is what we need to do to really figure out if there are habitable planets out there and life. Let me start by showing an old slide that was made by Chaz Beichman, one of your venerable leaders of this workshop. And he used to show this. I was a member of the TPF, Terrestrial Planet Finder Science Working Group back in the late 1990s, early 2000s. Chaz was the leader of that group. And he showed this slide. I've showed it in many talks that I've given since then. What it shows is this is flux, a measure of flux on the vertical axis on a log scale, wavelength in microns on the horizontal scale. Remember, the visible is 0.4 to 0.7 microns. The upper curve is what the sun looks like from a distance of 10 parsecs, and the bottom curve is what the Earth looks like from that same distance. And you see that the sun has just one curve there. It's basically a black body with a little Fraunhofer spectrum superimposed on it. And the Earth shows two curves. Of course, here down in the visible and the near IR, it parallels the sun's curve. That's because you're seeing the Earth in reflected light, whereas out here in the thermal infrared, you see the Earth from its own emitted infrared radiation. So this slide illustrates what's called the contrast ratio. This is one of two key parameters for direct imaging. In the visible, the sun is 10 to the 10th times brighter than the Earth. And that's a real challenge. You have to dim out the starlight by a factor of 10 to the 10th in order to see the Earth. In the thermal infrared, the sun is only 10 to the 7th times brighter. And I say only with quotation marks. It's still much brighter, but the contrast ratio is more favorable. So the initial thinking, in fact, when Chaz was running the TPF Science Working Group, we were focused on the thermal infrared region, as I'll show in a moment. But you have to weigh that against the diffraction limit here. You have to be able to separate the planet out spatially from the star. That defines an angle, theta, as seen from Earth orbit. And that theta is approximately lambda over d, where lambda is the wavelength you're looking at and d is the diameter of the telescope. If you go through the math, you find out, actually, I mean, real coronagraphs operate at some multiple of lambda over d, but you need roughly, say, let's say at TPF times, we needed 8 meters in the visible, and you needed about 80 meters in the infrared. So the techniques used in these wavelength regions would be different. Here's what we used to think about when Chaz was running the group at first. NASA's original concept was TPFI, Terrestrial Planet Finder Interferometer, and the initial concept was 4 2.5 meter telescopes on an 80 meter boom. This was patterned after SIM, the Space Interferometry mission, which Chaz mentioned in passing in introducing this workshop on Monday. So that's one way to do this. The disadvantages of both SIM and TPFI is that booms vibrate, and JPL learned about that by studying the SIM boom for several years and finding out that it vibrated on multiple different spatial scales and frequencies. So the Europeans picked up on this and studied space-based interferometry using a free flyer interferometer. Their mission was called Darwin. Alain Leger was the PI on that for many years. Unfortunately, both TPF and Darwin got canceled, but fortunately, both of them show signs of life. In fact, in Europe, the signs of life are called LIFE, the Large Interferometer for Exoplanets, which is now being studied. And I attended a Zoom seminar on that several weeks ago, and there's some very bright young people working on that concept again, which is good. Here's what you could get if you could do direct imaging in the thermal IR. This is, again, a very old figure. I think Chaz may have showed this back in TPF times. These are thermal infrared, medium resolution thermal infrared spectrum of Venus, Earth, and Mars in our own solar system. For Venus and Mars, you just see this very deep, strong 15 micron band of CO2. For Earth, you can see that same CO2 band, but you also see these water bands. That's a rotation vibration band of water. This is the pure rotation band out here. And you can see the 9.6 micron band of ozone. Ozone comes from the photolysis of oxygen. Oxygen is a potential biosignature, which we can talk about more in the panel discussion, but that would be very exciting if we could get a spectrum of an Earth an exoplanet like that.
Yeah, I hate to cut in, but we're running into the panel discussion. So,
okay, so let me finish off then by just saying that it was almost near the end here. So LUVOIR and HABEX are being studied. You can get spectra from those too. And there's a very strong oxygen band here at 7,600 angstroms or 0.76 microns, which could be seen by those. So let me leave it at that. I'll leave these conclusions up for a minute, but stop since I'm out of time. Thanks.
thanks, Jim. That's a great talk and a huge amount of material to have to get through in 30 minutes. We've got a bunch of questions. I'm going to punt most of them to the panel session, but there is one that's come up 3 different times in slightly different variations that I think it'd be useful if you can address now. So can you go back to the slide where you showed the carbon cycle with the volcano and the plate? Yeah. So there's a question. The question is essentially you had a statement earlier on that we don't care about subsurface water, but there are clearly interactions between subsurface materials. There's the feedback between the atmosphere and surface and subsurface systems. And then you also commented that about this limit cycling behavior. And in that context, is the Earth actually considered to be stable, or are we oscillating back and forth through ice ages and things like that, and not really stable? It's kind of a roll-up.
Let me take the second one first because I think it's easier. You know, the Earth has been we've been going through glacial, interglacial cycles for the last several million years, the Pleistocene ice ages. But these are little puny glaciations where the polar caps expand and come down to about 45 degrees latitude and then go back up. That's different from limit cycling where they go down to the equator and then you have to fully deglaciate. None of the models predict that the Earth would be or ever was in a limit cycling regime. So we do think that the Earth went snowball a couple times, but didn't do so repetitively. And we argue a lot as to why it went into snowball conditions. As for the subsurface liquid water, you know, maybe I'm too pessimistic. You know, there are people who think that there's methane in Mars' atmosphere, or at least that has been thought. And if so, and there are even people who think that that's a bioindicator. But if so, methane is present at something like 10 parts per billion if it's there at all. And you can barely see it from Earth with big telescopes from right nearby. So I don't think something like that would be detectable at all from a distance of several light years. And you know, I would love to be proved wrong by that, but that's my deep suspicion.
Well, it sounds like the question is not so much, or the answer is not so much one of feedback mechanisms between the atmosphere and the subsurface, but it's what is the amplitude of the signal that comes from subsurface material feeding back into the atmosphere, and is it actually a detectable one?
You know, it's pretty, as I think Lesney or Courtney said this morning, it's pretty difficult to see anything in Earth's atmosphere other than CO2, O2, and water vapor at medium spectral resolution. Methane is the fourth, you know, it's the other one that was talked about. You can't see that except in the visible, except at high spectral resolution. You might be able, and even in the thermal infrared, it's not so obvious. So those are produced in really large quantities at the Earth's surface. If you're getting leakage from a subsurface biosphere, any gas that comes from the subsurface is going to be present at much lower concentrations. I just don't think you can see it.